Hi everyone, I'm Rohit Kumar Singh, the teaching assistant for this course, Nuclear and Particle Physics. And this course is being taught by Dr. Paulos uh, at IIT Guwahati over the NPTEL portal. And this is the second live session. So, uh, in the last week, we talked about basic nuclear physics and quantum mechanics, sort of like prerequisite to the course. And there were some dots which uh, which I would like to you know answer now. Maybe I don't know if the student who asked those questions is joined or I don't know, but let's go over that. So first, okay, sorry, yeah. So first issue was this. Uh, this is the semi-empirical. So okay, so this is not. Let's. So this is a formula for binding energy, okay, and you all have studied it in the lectures. Uh, so all of you are familiar with this, right? This is from the week one lectures. These terms you are familiar with. So I'll go quickly over them. So if you have not understood them, so here this term here is this formula comes from the liquid drop model of the nucleus. So we consider nucleus as a liquid, as a drop of liquid, okay, with neutrons and protons in them. So sort of like a charged liquid made up of neutrons and protons, and we with some assumptions we arrive at this formula. So it's an empirical formula, okay. It's not experimentally driven. So how do we why are these terms here? Like there are one, two, three, four, five terms are there. So why are these terms here? Uh, so I'll go quickly over them. So the first term is just from the idea that binding energy should be proportional to the total number of nucleons. Like if you have more number of nucleons, then binding energy is just proportional to that, okay. And this constant, so this gives us this term, and this constant AV is for the volume. So because uh, so this is called a volume term, basically because we are talking about the whole nucleus, its bulk. So this is called the volume term, but it's just a constant, okay. It's a proportionality constant. Okay, but then we think that, so not all of the nucleons inside the uh, nucleus are in the same condition. For example, the nucleon on the surface experiences, different condition that than those who are in bulk. So nucleons in the on the surface get contribution only from one side, right? It feels strong force only from one side, not from the other side, because other side is empty, right? So then we might be overestimating the binding energy when we just write this term. So that's why we subtract surface term. Okay, and so why this 2 by 3 comes up? So you know that uh, radius is proportional to a uh, 1 by 3, and so r square gives you a to the power 2 by 3, right? And as is the proportionality constant again for the surface term. So that's why we subtract this surface term so that we don't overestimate with the volume term. Okay, now then comes this third term. So it is also subtracted. Uh, so this is due to the Coulomb force. So we know that the protons are charged particles, positively charged particles, and they will experience a Coulomb repulsion, right? And so each proton will experience the Coulomb repulsion due to all the other protons in the nucleus. So that's why uh, this term Jj minus Gg minus 1 is there. Uh, okay, and this is the Coulomb constant called AC. And we know that the Coulomb potential goes over like 1 by r, so that's why minus 1 by 3 is there. Okay, and then we have one more term here, which is the symmetric, which is a term due to symmetricity. So if you notice here, uh, okay, so let me write it a little bit differently. So we can take this A inside the bracket. So then it will be uh, uh, A 1 minus, okay. So now what do you see is, if uh, if Z is A by 2, this terms goes to 0, right? So this term is for considering that a stable nucleus should have equal number of neutrons and protons. I mean, should have half, should have J equal to A by 2. So this is another stability condition that nucleus has. So to incorporate this symmetry, we have this term, and if the nucleus deviates from this condition, then this term will contribute, and it will lower the binding energy. Okay, and then we have this last term, which is called the pairing term. So someone asked me about this term. I don't know who that was. Uh, uh, have you joined today? Okay, maybe he can watch the lectures later. So yeah, this term comes from this idea that a nucleus. Suppose you have odd number of uh, protons and odd number of neutrons. Okay, so what will happen is that uh, one of the either one neutron or one proton will decay into proton or neutron and then get paired together. Okay, so so if you have odd number of z and n, this will contribute positively. It will be a positive value. Okay, and if one of uh, neutron, suppose the proton is odd and neutron is even neutron, then it contributes to nothing because it has suppose one proton has nothing to pair with. I mean, even if it decays to neutron, it doesn't have any extra neutron to pair with. Okay, so that's why so this condition contribute to delta equal to 0. And if you have even z and even n, so uh, uh, this this is also this is already everything is paired here. So this term doesn't yeah, this also contribute positively. Yeah. So the interesting case is when you have odd z and odd n. So in this case, one of the neutron or proton can decay to proton and neutron and then pair with the one from the other subset. Okay. So I don't know. Do you understand this, or should I go over it again? Everyone got this concept? Why pairing term is there? Okay, thank you. So yeah, so then with this binding energy formula, we can write the. This is the semi-empirical. Sorry for my handwriting. Try again. Semi-empirical mass formula. Okay, so this is just mass of uh, mass of one proton into number of protons, then mass of neutron into number of neutrons, and subtracted by the binding energy, total binding energy of that is there for the nucleus. So this will give you the mass of the nucleus, and then you can what you can do is for a uh, particular mass number A, you can find a stable nucleus with with number of protons j. So to do this, just you have to differentiate with respect to j this term, put it to 0, and then you will get this thing. Okay, and then you can put the numbers to get you know these numbers are actually experimentally found, so these are there, and you can get the formula for the Z mean stable nucleus having proton Z. So this was, I mean, we solved some problems on this formula and concept, but yeah, I mean, I wanted to just go over it once again because it's a very important concept. Okay, so after this, one more thing I wanted to briefly discuss, uh, which was the concept of this probability current. So, in quantum mechanics, a probability current is defined by this formula. Mm, okay, and in general, it's a function of both spatial and time coordinate. So let's write it like this. No, someone asked me, I don't know if someone asked me, or if I asked myself. So, what is the physical interpretation of this formula? So, let's, so, so I'll write an equation. Uh, so, here, the PAB is the probability of finding a particle. So we are talking about one dimension, okay? So just one dimension x in the range A to B, okay? Just 2 points at time t, okay? And so then what does this tell you? So this means that the probability current density J is just the rate, okay, at which this probability is flowing, okay, like the current flow. I mean, that's why it's called probability current past point x, okay, any point here you can take. And if this if this sorry, so uh, not this. So if J is increasing, suppose, so what can you say? So it will mean that more probability is flowing on one side, right? So suppose here this side, suppose this is your x. So if this comes out to be increasing, then the probability of finding the particle is flowing to this side. Okay, so that is the physical interpretation of this probability current. And if it is constant, then the probability of finding the particle is constant over everywhere. So this was the basic concept. So I hope now it is clear for everyone.
Sir, I had a question, sir.
Yeah.
So then, what is the significance of finding the probability current? If we have the probability of finding the particle within AB limit,
Mm-hmm.
then can we say that the probability current gives us the change in the probability?
Yeah, that's what the rate at which the probability is flowing. So rate of change of the probability. Yeah, exactly.
So, with respect to time, the rate of change of probability.
Yeah, yeah, that is.
And this is also in terms of probability only, like in terms of percentages.
Yeah. It's a probability. So you have normalized wave function. So it's 0 to 100% will be there. Okay. So that is all that I wanted to discuss from last week. So in week two, we have mainly cell model, which are I mean the lectures of at NPTEL, uh, mainly contains the cell model, and I think some concept of scattering. So I couldn't keep any problem from a scattering. I don't know which problem to keep, but yeah, scattering is a very important concept. You should read maybe some maybe first basic quantum mechanics, and then scattering is there in Griffith's quantum mechanics, very well written. So first you should go over that, and then you will be able to understand the lectures more. And then then there is cell model, obviously. So yeah, cell model is uh, an analogy of the atomic model, which is there for the electrons, and similar to that we have so similar to what we have in atomic model, the different cells in which electrons are grouped together. So similarly to that, we have in nucleus, we have nucleons grouped together in cells. Okay. And so there are well defined quantum energy states, taking into consideration the Wood section potential and the spin orbit coupling. uh, so for example, okay, let me there is one problem we have I wanted to solve. Okay, so yeah, so cell model, all of you have gone through the lectures, right, of cell model. Anyone who has not yet gone through the lectures? If anyone has not gone through, please raise your hand. I can briefly, explain, try to explain it more. Okay, one I see one raised hand. Two. Okay. So okay, so let me just quickly go to the. Let me just quickly review the cell model then. Okay, then we will solve some problem. But first, before solving, before going to the cell model, I wanted to solve simple problem uh, uh, based on this binding energy formula that I written. So I don't know if so should I need to solve it, or is it trivial for you at this point? Please answer. Then accordingly I will proceed. So should I solve it, or should I leave it?
Sir, if binding energy is higher, then that's the most stabler one, right?
Yeah,
That's it.
yeah, 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 that is what. But yeah, I mean, the formula is there. This you can use just this formula. Everything is given here. AV, AS, AC, asymmetry, and AP pairing term, and this delta is just plus minus AP. So, uh, so everything is given. You can just put these things in this formula, and you can calculate, and I will just so here also in the formula you need A and J. So here that is also given for both beryllium and boron. So this should be not much problem, right? So so if you think you can do this, I will skip it for now. Okay. Uh, just try it out, and we can discuss it. If you're not able to do the calculation, just let me. It should be very simple. Everything is given. Okay. so so then one problem is there from the cell model. So we have to find the spin of ground state of fluorine. Okay, nucleus of fluorine. So here number of protons is 9, and mass number is 17. So number of neutrons is 8. So as I told you before, so in atomic model, what we have is different cells. So uh, you must have studies K, L, M, these cells, and these hold electrons. So 2, 6, uh, like this, and you get a stable configuration out of some there are some magic numbers in the atomic model. I don't remember exactly what are those. So similar to that, so what the idea of the cell model is that uh, you take a atom, okay, and you bombard it with some radiation. You will find that some atoms are easy to ionize than others. So people found that those atoms which have a particular configuration, so suppose some atom has 261 configuration and some has 26, so it will be easier to ionize this one than this. Okay, I mean, ionize means to remove one electron. So that gave that gave the idea that there must be a cell structure. I mean, there should be a closed cell in which the atom has a stable configuration. So similar to that, nucleus also nucleus are also found to be behaving like this. So uh, when nucleus are bombarded with uh, particles, like bombarded with neutrons or something, people found that some nucleus tend to break easily, and some were more stable and did not break easily. So based on that, they made this cell model. Okay, and so the cell model incorporates both the not only the so so there should be some potential which is required to bind the nucleons together. So suppose one nucleon in the nucleus must experience some kind of attractive potential, some kind of uh, attractive potential basically. So in order to stay in that in that confined place. Okay, and that is called the Wood-Saxon potential. I don't know if it has been discussed or not. And but this is not enough. So because the Wood-Saxon potential, and we know from quantum mechanics that you can write you can is given a charged particle in a potential, you can write the energy states, right? That everyone knows, right? From the solving the Schrodinger equation, you can do that. And but there comes another potential, which is spin orbit coupling. So spin orbit coupling uh, introduces another it gives an extra term into the potential, and it further split the uh, energy levels. Okay, so finally what you have is uh, a cell model with different energy states. So I'll write those here briefly. Some states I'll write. So you have 1s. So 1s means that uh, you have, so 1s means that the angular moment, so the azimuthal angular momentum is of this state is 1, and and uh, this can hold 1/2, because s state can have just sorry. So uh, 1s state cannot be split, so it's just is spin number is just one and half, sorry, half.
It
And
seems,
yeah.
sir, angular momentum for S is zero, right?
uh oh, sorry, yeah, sorry, I meant n is 1. Yeah, sorry. Yeah, n is 1 and then l is 0. Yeah, right. And here spin is written by J, not by S, so just keep in mind. Okay. And oh, sorry. And the uh, number of fermions that it can accommodate is given by the quantum rule, 2J by 1, which will be 2, right? So this state will hold two fermions basically. So two neutron or protons can be there in this 1s states. Okay. So after this comes the 1p state, and it can split into two. So 1p half, uh, and the splitting is based on, the further, like this scale is energy. Okay. So the so the spin orbit coupling basically, you know uh, there is a term in quantum mechanics called degeneracy. So it breaks the degeneracy and gives you these two states out of this 1p state. And you get 1p 3 by 2. Okay. So like this, you have further, high energy states, and they also split accordingly, and uh, you get the cell structure that you get in atomic model. Okay. So so to solve this question, okay, uh, we need also, so one thing you have to consider here is that uh, in cell model, there is one very strong assumption is that uh, that nucleus, that nucleon, either proton or neutron, uh, will be considered which is not paired. Okay. So that will govern the whole spin, I mean, property of the nucleus. Okay. uh, like I said, for an inert atom, for a helium, in case of atoms, just one electron in the valence shell, changes its whole properties, how it will react to other atoms, and how will it, like, why oxygen is so much reactive and why helium is not, or not helium, why inert gases are not. So it's just because this valence electrons in the outermost shell, right? So that's what happens in the nucleus also. So here we will not consider the neutrons, because they are paired together. But proton has one left out proton, because eight are paired, then one is not paired, and this one extra proton, okay, uh, will govern the uh, property of this nucleus. And so how will we uh, how will we distribute this among these energy cells? So let me again, let me write it little bit more carefully. So 2 can come here, and then 4 can come here, uh, 2 again come here, and then we have 1d splits into uh, so 1d splits into 5 by 2, right? So 6 can come here, so I think that is enough, right? So we have 9 protons, 2 4 2, that is 8, and 1 can go here, right? So uh, so the outermost sorry, so the unpaired uh, proton will be in the 1d 5 by 2 state. Okay, what does that mean? So this means that, and it has n equal to 1, L equal to 2, and J equal to 5 by 2, right? So the spin will be, as you can see, it will be 5 by 2, simple. And uh, yeah, and this will govern, I mean, this spin will be for the whole nucleus. Okay, it will govern the whole nucleus. Like if two nucleus will come together, they will interact through this kind of spin. Okay, so this is most crucial part of this cell model. Okay, it is not that this is just the, it is for the whole ground state of this nucleus that this spin is there. Okay, it is governed by this just the one unpaired proton. Okay, so has anyone any doubt here? Yeah, thank you. I mean, those who couldn't understand, like, I tried to briefly, just give you a rough idea of what this cell model is. Uh, I mean, I cannot go over to the whole detailed theory. You should go and watch the lectures and then come back to the problems. It's a simple concept. I mean, but yeah, the essential thing is this one, like the unpaired nucleon govern the, you know state of the whole nucleus. Okay, so similar problem is there. So same fluorine nuclei, and we have to find the parity. So we just found out that the state in which the unpaired proton will lie is 1d 5 by 2, right? And L is 2, and we know that parity is given by -1 to the power L, right? So it will be 1. So this means that it is even parity. Is it okay? Okay, thank you. Now there is one interesting problem. Okay, which of the following is a possible spin value of the first excited state of neon? Okay, nucleus. So here we have 10 protons and 11 neutrons. Now, as I mentioned, so here this will this will be irrelevant to us. This will govern the everything about the nucleus. Now let's again try to find the where the neutron will lie in which just first let's write the ground state. Okay, so let me draw the cells again. 1s, so we need 11, right? 1p, so 1 is half, 1p 3 by 2, 1p half, then we have 1d. I think that will be enough, right? 2, 4, 2, and then 6. 1d 5 by 2, right? And then there are further splitting, but so again we have to write because we want to calculate the excited states, right? So 1d 3 by 2, and then there is a 2s state which comes in between. Okay, its energy is lower than the 1d 3 by 2 state, so here 2 will go, and then here 4 neutrons or protons can go. So this is the ground state configuration is 1d 5 by 2, right? Now what could be the excited state? Should it go to 2s 3 by 2 or 1d 3 by 2? What do you guys think? Anyone?
Sir, it will go to S, the 2S 1 by 2.
Okay. Sorry, 2s 1 by 2. Yeah.
Sir, or can the nucleon from the 1p 3 by 2 be split with its partner and go to 1d 5 by 2?
Uh, hmm. Yeah, that is also a possibility. Because see, no. Mm,
So, like, we need the energy separation between 1d 5 by 2, 1p half, and 2s half, and 1d 5 by 2. Whichever is greater, that will not be taken.
yeah, yeah, yeah. Yeah, I mean that is the concept. I remember something interesting happens with this nucleus. I'm not sure if this is true that it will go to 2s 1 by 2. I think something more interesting will happen here. Do you guys know, or
Sir, is it related to the deviation that occurs from extreme single independent particle, or that is not relevant here?
Uh, yeah, that can also be a factor here, but yeah, this is a. I think this is a very in. This is this problem was from last year's assignment. Okay, of this course, and there should be some interesting thing here. But let's for now let's assume that it goes to 2s. Okay, so 1 by 2 will be the spin value, but I'll dig about it more, and maybe we will discuss next time. Okay, I think what you're saying might be true. Maybe some peculiar thing will happen here to in order to have a lower energy configuration, but I'm not sure uh, right now. Okay.
Yeah, so because if the 1p half nucleon goes and sits in 1d 5 by 2, then we'll have two unpaired nucleons. So
Yeah,
there we'll need that quantum mechanical sum of both the spins.
yeah, yeah, right. Hmm. Yeah, I think I have seen this problem somewhere else. I mean, I don't remember. This is some exception kind of uh, thing that are there. There are two, three interesting exceptions. I think this is one of those. Maybe I'll try to dig about it. Okay. Uh, uh, so yeah, for now let's move on. Okay, so here we have to calculate the orbital quantum number L uh, of the ground state of this same nucleus. So I think this is now again trivial, right? We just found out that L should be 2. So I don't know why it is there. Okay. So yeah, I wanted to keep today's session very short because I'm not feeling really well with my cough, and so. But yeah, we can. Do you have anything else to discuss? We can discuss briefly if you want to discuss
Sir,
anything. Yeah.
sir, I had a doubt regarding the spatial meaning of the shell model.
Spatial meaning means.
Like for example, like in atomic shell model, the the electrons that sit in the lower shells are
Mm-hmm.
closer to the nucleus.
Yeah.
So what about inside the nucleus? When we assume the same shell sort of shell structure,
Mm-hmm.
what is the spatial orientation of nucleons that are occupying lower shells, and as they increase, the shell uh, becomes higher, like the spatial configuration changes, or it's just random?
I see. I I get your point. So yeah, in case of electron, it's in case of atomic model, it's very you know uh, intuitive to think about it. Like yeah, so there should be a valence cell. I mean yeah, electron closer to the nucleus will have stable configuration. Further more it goes, there will be a screening from the uh, electrons in between, and so That's how you get the unstable configuration, right? But
Yes, sir. Yes, sir.
yeah, but but in the case of nucleus there is not a such thing. But there is one thing is the there that so the strong force is a very, short range force, right? And Coulomb repulsion is a very long range. I mean, Coulomb repulsion has infinite range, right? But the nuclear force has a short range. So you take one neutron or proton inside a nucleus, okay, and so it depends at which at which place inside the nucleus this neutron or proton is lying. So suppose this is your nucleus roughly, and you have distribution of neutrons and protons. So so the concept of cell is there because it's completely due to experiments. So as I told you, the experimentally people observed that if certain number of neutrons or protons is there, the nucleus is hard to break. Its binding energy is basically higher. And so to understand that, so you are asking, how it could, how we can draw an analogy like in atomic model. So, so suppose one nucleon is here, okay, and it will experience forces. So, like in the binding energy, when I was discussing the liquid drop model, I mentioned all the forces that are there for a particular uh, nucleon inside a nucleus, okay, and all these forces will uh, kind of lead to a configuration of the distribution of those nucleons inside the nucleus. As far as I can, you know, understand this. So this is all, the interplay between the uh, strong and Coulombic forces. And here you can visualize. So as you have nucleus in atomic model, in the cell model, uh, the rest of the nucleus is what is what is giving you this cell structure for that one nucleon. So because this splitting that I wrote, this energy levels that I wrote, it's for a single, it's for it's for to occupy a single uh, uh, neutron or proton at the end, right? The excited state. The outermost cell. So, this splitting is there because of this potential, and this potential is because of the rest of the nucleus other than the one that you are talking about. And this energy level is because of the Schrodinger. When you solve the Schrodinger equation, considering that one uh, nucleon in mind, okay, and taking the potential of all the other nucleon inside the nucleus, and which gives you the Wood-Saxon potential. Uh, You solve the Schrodinger equation, you get these states, and when you apply the spin orbit coupling, you get further splitting. You break the degeneracy of these states. Do you get an idea? I mean, what I'm saying?
Yes, sir. Yes, sir.
Yeah, so I mean, this is what happens basically in nucleus. You cannot, yeah, it is little counterintuitive, but I mean, that's how you can go about it.
So can we say, like, unlike the atomic shell model, where the shells are inner and they expand outwards in a spherical manner,
Mm-hmm.
here individual nuclei have certain regions where these shells are present, but they are not fixed pattern.
Yeah, here, I mean, no one can see the see the pattern, or no one has observed any such kind of pattern. Like, uh, in the atomic model, now people can visualize the states, S states, P states. You can visualize it nowadays experimentally, right? But for the case of nucleus, that is not the case. I mean, it is impossible to do that. But still, because quantum mechanics allows for it, so there are these states. But how how the how the nucleons arrange themselves to achieve this? Uh, I don't know if there is any uh, idea about it. Yeah,
God, sir, God.
yeah. Because the nucleus is a very packed structure. It's very dense and packed. So I'm not sure. I mean, obviously it is not static. It changes its shape, but there's nothing spinning. I mean, no nucleon is spinning in term in relative to other nucleon, and such things like orbital angular momentum of a single nucleon with respect to rest of the nucleus. That kind of concept is not here. So you cannot think about it exactly as the atomic model. So that is very difficult to imagine.
So then there must be like some sort of discrepancy with this model, right?
Yeah, obviously this is not a perfect model. There are many discrepancies. I think uh, I don't know which one is. I mean, I don't know which do they teach a model more sophisticated than this or not, or just we take this model to be our best. I don't know. I'm not a nuclear physics expert, but yeah, this model has many exceptions. So like I was saying, this I think this is one of the exception. Like what happens here, instead of going it to 2s half, it goes somewhere else and something happens. Like uh, it has some flaws. Like it's not perfect. Yeah, there are some exception. I don't remember exactly. Okay, so anything else you want to discuss? So yeah, the cell model I think doesn't incorporate the electric quadrupole moment of nucleus. That is also one thing. So when you incorporate the quadrupole moment, then further splitting happens, and then I think yeah, that should be the final model or something. Yeah, something more is there than this cell model. I mean, beyond the spin orbit coupling, you have quadrupole moments of the nucleus. Yeah, but I don't know if those are in the scope of the syllabus. Okay, so if you have no further questions, thank you everyone for joining today. Let's meet again next Saturday. Okay, bye.
Thank you, sir. Bye, sir.
Bye. Bye everyone.